Hello, welcome to the Learn English Lab. Today's podcast, Advanced English Listening Practice podcast topic name is 30 plus C1 level vocabulary on mathematics. We are diving deep today looking at the language behind logic, behind calculation, quantification really, and the goal. To boost your English C1 skills using the very precise words of mathematics.
That's exactly it. Making that jump, from intermediate to advanced English, well, it often means getting comfortable with complex areas, and math gives us some incredibly specific, rigorous vocabulary. So this deep dive, it's really designed to give you, the listener, more than 35 pretty powerful terms. And these aren't just definitions we're rattling off. These are actual tools you can use to talk about, well, anything from advanced geometric modeling, statistical analysis,
all the way to financial reports or even global commodity trading.
Right. Enabling that really nuanced expression you need in academic settings, scientific discussions, professional chats. It's about precision.
And we're not just running through a vocabulary list here. We want to synthesize this. So yes, we'll define the terms, absolutely. But then we want to jump straight into how they're used in the real world. Those surprising dual meanings sometimes that give these words real power. We're trying to move beyond the basic calculator stuff into, well, analytical thinking.
A good way to put it.
So to structure this so you can really absorb it, we figured we'll start with the physical side of things, the building blocks, measurement, shapes. Then we'll move towards the more abstract ideas, the concepts that define relationships. Sound good?
Sounds like a solid plan. Let's get started.
Okay, let's unpack this. Starting right at the beginning, really. Dimensional descriptions. When we look at circles, spheres, anything round, there are two terms that are just absolutely fundamental for measuring them precisely: diameter and radius. Now, they might seem elementary, basic even, but using them properly at a C1 level, that means understanding where they actually matter most.
Absolutely. These two, they define the scale of anything circular. So the diameter, that's the full span, right? The straight line cutting right across the widest part through the center, joining opposite sides.
The width across, basically.
Or the central line of symmetry, you could say. But think about its importance in engineering. If you're bundling, say, a bridge arch or designing a turbine, the diameter of those parts, it dictates structural integrity. It dictates material stress.
Ah, I see. So a small change makes a big difference.
Oh, huge. A tiny increase in diameter can exponentially change how much load it can bear. It's not trivial at all.
And then its partner, the radius, the little brother, as I think of it sometimes, that's just the length from the center point out to the edge, the boundary.
Half the diameter. Or the radial distance is the technical way to put it.
We often take it for granted, I think, but that measurement is so crucial for anything that rotates. For you listening, think about cars, vehicle mechanics. The radius of a tire, it doesn't just affect the turning circle, how tight a U-turn you can make, which is a key spec.
Right, for maneuverability.
Exactly. But it also affects the speedometer reading. The car calculates distance traveled based on wheel rotations, assuming a certain radius. If the radius is off, the speed reading is off.
That kind of precision is absolutely key. And speaking of relationships, let's talk ratio. Now this term, it expresses that quantitative link between two amounts. It tells you how much bigger or smaller one value is compared to another.
So it's about proportion, yeah. Or a quotient, maybe, the relationship between numbers. And the beauty of ratio, I think, is how it works across the board. From really simple things to super complex analysis.
Totally.
Like you might use a simple ratio when you're baking, adjusting ingredients, aiming for, a 2-to-1 ratio of chocolate chips to walnuts in your cookies. Simple.
Easy enough.
But then, boom, you pivot instantly to something like complex financial analysis.
Exactly right. Suddenly, we're assessing the health of a whole company. Analysts aren't just looking at the raw profit number. They're calculating critical financial ratios, things like the debt-to-equity ratio or the current ratio. These tell them about a company's stability, its liquidity.
Compared to others in the same field?
Precisely. They act as benchmarks. Is this company carrying too much debt? Is it operating efficiently compared to its competitors? These ratios tell that story. Or, shift fields again in physics. The mass-to-light ratio is vital for studying dark matter. It's a term that really demands you understand the context.
Okay, moving from those relative comparisons to something more about absolute precision, let's look at decimal. This is how we represent a fraction using a base 10 system marked by that little dot, the period.
Or a fractional number, a point numeral, you could say. And yeah, we see them constantly in pricing, that classic 9.99 cents or £19.95.
Everywhere.
But their real C1 importance, that lies in scientific accuracy. In research, the number of decimal places you use isn't just Incidental, it's a communication. It signals how meticulous the measurement was.
Ah, so more decimal places means more careful work.
Generally, yes.
Yeah.
If you report a distance as, say, 3.14159 meters, that implies much greater precision, much less potential error than just saying 3.14 meters. Those tiny digits, they define the limits of your instrument's accuracy. They speak to the repeatability of your experiment.
That idea of precision, it leads us perfectly into two terms that, honestly, students mix up all the time. But they have distinct mathematical weight: equation and formula. We really need to draw a clear line here.
You do. It's a common confusion. An equation is fundamentally about equality. It's a statement saying two mathematical expressions have the exact same value. It demands balance. When you solve, say, a quadratic equation in algebra, you're finding the specific values, the conditions that make the left side equal the right side.
Like balancing scales.
Exactly. Physicists use equations to show relationships between quantities, like the famous EMCC. The whole point is finding that equivalence, solving for an unknown to keep things balanced.
Okay, so that's equation. What about formula then? How is that different?
A formula is more like the rule or the law itself. It's an established recipe, an algorithm, usually shown in symbols and letters, for calculating a specific value. You use a geometric formula to find the area of a rectangle. Area equals length times width. That's the rule.
Or chemical formulas for molecules.
Right. H0 is the formula for water. It defines the composition. So maybe think of it like this. You use the correct formula to know the method, but you might end up solving a complex equation to get the final numerical answer using that formula.
Okay, that helps. Formula is the how-to, equation is equal to.
That's a decent shorthand. Getting that distinction right is really crucial for clear academic communication.
And finally, for this first section on foundational stuff, let's touch on subtraction. The process of finding the difference, deduction, the minus operation. Obvious uses spring to mind, right? Figuring out a budget shortfall, counting remaining stock. If you started with 100 widgets and sold 17, subtraction tells you what's left.
Standard arithmetic.
But the really interesting application, the C1 level nugget, is hidden away inside computers, isn't it?
It is, and this is where it gets quite technical but really cool. If you connect this to computer science, subtraction, specifically binary subtraction, is fundamental to how microprocessors work. See, computers don't typically do subtraction directly like we do with pen and paper. They mostly use addition circuits because they're simpler to build.
So how do they subtract them?
Clever trick. To calculate a minus b, the computer actually adds a to something called the 2's complement of b. It's a way of representing negative numbers in binary. This technique effectively turns subtraction into addition. It makes the hardware simpler, faster, and that little process, it underpins basically all digital math, from your phone to a supercomputer.
Wow. So subtraction is actually addition in disguise for computers.
In a manner of speaking, yes, it's foundational stuff.
Right. This is where, for me, it starts to get really interesting. We're moving away from just calculating quantities into more abstract math, the concepts that define how things relate to each other, the dependencies. Let's kick off with function.
Function. Yes.
Yeah.
This is absolutely the backbone of mathematical modeling. A function describes a rule, a consistent relationship, where one quantity's value changes based on the value of another quantity. Think of it as a mathematical mapping or a dependency rule. When you hear function in an academic context, your brain should immediately jump to thinking about causality, predictability, relationships.
And we use them to model and predict. Well, pretty much everything, don't we? In visual math, you graph the function to see its behavior. Is it a straight line linear, a curve quadratic? Maybe it shoots up exponential?
Exactly. And in computer science, it's very direct. A programming function is a block of code. It takes some input data, runs a defined process, and reliably produces a predictable output based on that input.
Input, process, output. The function defines the process.
Correct. And if we jump over to economics, functions are just essential for modeling abstract concepts. The classic example is supply and demand. The quantity produced is often modeled as a function of the market price.
Right. Price goes up, supply might go up too, following a functional relationship.
But where it gets really C1 level complex is when you deal with nonlinear functions. Think about compound interest in your savings account. That's an exponential function. The growth isn't steady. It accelerates rapidly over time.
Or like modeling disease spread. That can't be linear.
Definitely not. Epidemiology relies heavily on understanding complex, often nonlinear functions. How does the infection rate relate to population density or vaccination rates? Those are functional relationships. The term function lets you talk about these dynamic, complex changes very precisely.
Okay, so to really understand a function, we need its components. Let's bring in those algebraic essentials, value and variable. Let's try and pin these down clearly. Value, that's the specific number, the amount that a symbol or letter represents at a particular moment in a problem.
A concrete number.
Right. Whereas the variable is the symbol itself, the placeholder, usually a letter like X or Y, that is capable of taking on different values within that calculation or function.
Yes. And the interplay between them, that connection, is everything in problem solving. In algebra, we usually assign a specific value to a variable, like x equal 5, to then solve the equation.
Find the unknown.
But the variable really shines in scientific experiments. The independent variable, that's the thing that scientists deliberately changes or manipulates. The dependent variable is what they measure. Its value depends on, is a function of, the changes in the independent variable.
Cause and effect mapped onto variables.
You got it. And we absolutely have to mention absolute value here as well. It's related but distinct.
Yes, the value ignoring the negative sign.
Exactly. It's critical when you're talking about things like distance, magnitude, or error margins. It describes how far a number is from zero, regardless of direction. If your experiment result is 5 degrees Celsius off the target temperature, the absolute value of the error is 5, whether you are 5 degrees too hot or 5 degrees too cold. It focuses purely on the magnitude of the difference.
Okay, makes sense. Distance from zero.
Right. Now, shifting gears slightly, let's look at the parts of division and multiplication that carry some serious weight outside of basic sums. Factor, dividend, and divisor.
Okay, the setup for a division problem. The divisor is the number you're dividing by. The dividend is the number being divided. Pretty straightforward roles.
They are. But let's start with factor, because that one has incredible depth and application beyond simple arithmetic.
Right. Mathematically, a factor is a number that divides another number perfectly, with no remainder. 2 is a factor of 10, 3 is not.
Correct. And in number theory, a whole branch of mathematics, we break down composite numbers, like 12, into their prime factors, 2 by 2 by 3, to understand their fundamental building blocks. This is crucial for everything from cryptography to generating complex sequences.
But the word factor, it just explodes out of pure math, doesn't it? In a C1 context, it basically becomes a synonym for component or contributing cause or element.
Absolutely. We talk constantly about environmental factors affecting climate change, or socioeconomic factors influencing election results, or risk factors for a particular disease in medical studies. It becomes a key term for analysis and causality in almost any field.
Identifying the parts that contribute to a whole outcome.
That's a great way to summarize it. And now for that fantastic dual meaning, the one that often gives listeners a real aha moment, dividend.
Okay, arithmetically, it's just the number being divided up. Simple.
Simple, but jump over to the world of finance and investing. Suddenly, dividend means something completely different. It's the portion of a company's profits that gets paid out, distributed to its shareholders.
Ah, the payout. Right. Yeah. Nothing to do with dividing a number in the mathematical sense.
Almost nothing. Conceptually, maybe a share, but practically no. You'll read headlines like, "Tech giant increases quarterly dividend." That's about sharing profits with investors, part of their investment strategy.
And investors track that closely. They calculate the dividend yield, right, to see the return they're getting from those payouts relative to the stock price.
They do indeed. So using dividend correctly in both contexts, the math context and the finance context, that shows real C1 lexical mastery. It retains a subtle sense of a shared portion, maybe, but the application is worlds apart.
That context dependency is huge. Okay, and to wrap up this section on abstract bits and pieces, the broad adjective, mathematical, meaning simply related to or used in mathematics. Arithmetical, numerical, algebraic, it covers the whole field.
It's the umbrella term, and its use signals the application of quantitative structure or logical reasoning. We talk about highly complex mathematical models being used to predict weather patterns.
Or now, even things like optimizing global shipping routes, right? Complex logistics.
Exactly. Or you might pursue a mathematical career that could mean pure research in academia, or it could mean applying mathematical theorems to solve very real-world problems in engineering, finance, data science, cryptography. It labels any field built on that quantitative logical foundation.
A sophisticated label for number-based or logic-based.
Pretty much, yes.
Okay, let's shift focus now. We're going to explore the C1 vocabulary we use to talk about size, about scale, about limits, everything from the tiniest possible amount to the idea of something truly unbounded. And we'll start at the small end.
Minimal.
Minimal. It means very small in amount or degree. Crucially, it often implies the smallest possible or the least necessary amount. Synonyms could be negligible, slight, or least. In fields like engineering or manufacturing, the constant goal is often minimal waste or minimal energy use. It's about optimization, efficiency, driving efficiency, sustainability. And in science, the quest is always for minimal error, right? You want your measurements to be as close to the true value as possible with the least deviation.
Absolutely critical. In high-stakes areas, think aerospace engineering or quantum physics calculations, even a seemingly minimal miscalculation, a tiny error, could lead to catastrophic failure. So minimal implies this targeted reduction. You're not just aiming for small, you're aiming for the least possible deviation or resource use. Operating with minimal resources means you're being highly efficient, highly optimized.
Got it. Less is more, but strategically so. Okay, next. Numerical. This just describes something represented by or relating to numbers. Quantitative. Digit-based.
Yes, the language of data, of evidence. In research, you can have a great hypothesis, a brilliant theory, but without solid numerical data to support it, it remains speculative.
Just anecdotal, right? If a report doesn't have the numbers, its claims are weaker.
Much weaker. And think about our digital world. Everything, ultimately, is broken down into numerical codes. Secure online transactions, encryption, data transmission, it all relies on incredibly complex numerical algorithms working behind the scenes.
Numbers running the show. Okay, now for a tricky trio. 3 words that deal with vastness. Countless, endless, and infinite. They often get used interchangeably in casual speech, but in more formal or technical language, they have important differences.
They certainly do. Let's start with countless. This implies a number so large, so numerous, that it's practically impossible or not worthwhile to count. It suggests great abundance.
This one more descriptive, less mathematical. Like you might get countless emails after a presentation, or you look up at the night sky away from city lights and see countless stars.
Exactly. Synonyms might be innumerable or myriad. It implies a practical inability or unwillingness to count rather than a theoretical impossibility.
Okay, countless is too many to bother counting. What about endless?
Endless usually suggests something going on, seemingly without limit, often in terms of time or space. But it doesn't necessarily mean mathematically unbounded in the way infinite does. You might describe a desert landscape as stretching out endlessly to the horizon. Or maybe a tedious bureaucratic process feels endless because it's taking so long.
So it can be more metaphorical,
Right.
perpetual, boundless.
Often, yes.
Yeah.
It emphasizes the perception of lacking an end, whether in duration or physical extent.
Right. But now, the big one, infinite. How is that mathematically different from just countless stars or endless desert? If a mathematician says the number of points on a line is infinite, is that the same as saying there are countless grains of sand on all the world's beaches?
That's the crucial distinction. And nailing this really shows C1 understanding. Countless refers to a very large, but ultimately finite number that we just don't count. Grains of sand, however many trillions there are, it's a finite number. Infinite, however, is a precise mathematical concept. It means truly unbounded, limitless, having the property that it can be continued forever without end. The set of all whole numbers, 1, 2, 3, is infinite.
So countless is practically uncountable. Infinite is theoretically unendable.
That's a very good way to put it. Infinite operates on a different conceptual level. We see it in calculus when we study the behavior of infinite series sequences of numbers added together forever. Do they converge to a value or diverge? Pi is another famous example. Its decimal expansion is infinite. It goes on forever without repeating.
And the big cosmological questions, is the universe itself spatially infinite or just incredibly, incredibly vast, but ultimately finite?
Exactly. That's a fundamental debate where the concept of infinite is central. So the term requires a grasp of limits, or the lack thereof, that countless and endless simply don't.
Okay, that clears things up significantly. Finally, for this section on scale and order, ordinal. This refers to a number that indicates position or sequence in a list. First, second, third, and so on.
The ranking numbers. They impose structure, order. We use ordinals constantly without even thinking about it giving dates, like the 4th of July or the 10th of December.
Or ranking runners in a race, first place, second place, third place, establishing that hierarchy.
Precisely. And beyond just everyday ranking, ordinals are vital in computer science and more abstract math for ordering data structures. In database systems, records often need to be sorted based on some ordinal property, maybe the sequence they were entered in or their assigned priority level. And in set theory, a very abstract branch of math, ordinals are used to define and compare the order types of different well-ordered sets, basically structuring infinite collections in a rigorous logical hierarchy.
So from simple ranking to structuring infinity, ordinals cover a lot of ground.
They do indeed.
Right. Let's move now to how math gets applied visually and physically. We'll look at the symbols we use for clarity, some specific geometric shapes, and then dive into a whole range of measurement units, some standard, some quite specialized, even historical. Hashtag A, notation and shape. Terms 1922. Starting with notation, a simple but vital one, bracket. Usually the square ones, sometimes parentheses, used to group things together, right?
Exactly. Their main job is clarity and order. In a mathematical expression, anything inside brackets must be dealt with. First, they enforce the order of operations. So 5, 2 plus 3 means you do the 2 plus 3 first, essential for avoiding ambiguity in complex calculations.
And they're used in other ways too.
Yes. In linear algebra, brackets are often used to define the elements of a matrix. And outside math, think about academic writing. You often see square brackets used within a quote to insert a clarification or indicate a change, or sometimes for citations. Their function is always about grouping or setting something apart.
Okay, clear. Now, geometry. Two terms related to shape and space, segment and solid. Let's start with segment. Geometrically, it's defined as a part of a circle cut off by a straight line, a chord.
That's the pure geometric definition, the circular section. But that idea translates directly into how we visualize data. Think of a pie chart showing market share, each slice representing a category's proportion. That's a segment of the whole pie.
Ah, right, a data segment.
Exactly. Or in engineering, if you're analyzing a curved bridge support or part of a dome, you might analyze it as a segment of a larger theoretical circle or sphere, applying specific calculations for stress and load on that segment.
Okay. And solid. This seems more straightforward. A three-dimensional figure, something with volume, height, width, and length.
That's the core of it. Cubes, spheres, pyramids, cones. These are all solids. The key contrast is with flat, two-dimensional shapes like squares or circles. Solid occupy space, they have volume, potentially mass.
Which makes them relevant for building things.
Absolutely. Construction, manufacturing, physics. Engineers need to calculate the volume, density, or surface area of solid objects, maybe designing an engine part, figuring out how much concrete is needed for a foundation, or calculating the buoyancy of a ship's hull, which is a complex, solid shape.
Got it. 3D object with volume. And one more in this notation shape group, the verb to express. In a mathematical or formal context, what does this mean?
To express here means to represent or state something clearly and precisely, often using symbols, a formula, or a concise statement. It's about formal representation. Synonyms might be to denote or formulate.
So a teacher might ask a student to express a complicated fraction in its simplest form.
Exactly. Or a scientist needs to express a very large measurement, like the speed of light, using scientific notation like 3 by 10 arrows, because it's more concise and standardized than writing out all the zeros. It's the verb you use when you're talking about the act of representing a mathematical idea formally. Hashtag TAD-B, unit conversions and application. Terms 2333.
Okay, before we hit the really specific units that link math to industry and history, let's quickly cover to total. Seems simple to add everything up.
Pretty much. It means to sum, to aggregate, to find the overall amount by adding up all the individual parts or numbers. Pure aggregation.
Used everywhere, I suppose. From personal finance totaling your monthly expenses.
Right up to the highest levels of business. A CEO needs the report showing the total sales figures for the quarter. An accountant needs to total up assets and liabilities on a balance sheet. It's the universal verb for finding the quantitative whole.
Simple but essential. Now let's talk standardization. The metric system.
Ah, the metric system.
Yeah.
Officially known as the International System of Units, or SI, it's the globally agreed upon standard for measurement, built primarily around the kilogram for mass, the meter for distance, and the liter for volume.
And its big advantage is it's decimal based. Everything works in powers of 1,000 centimeters in a meter, 1,000 meters in a kilometer, 1,000 grams in a kilogram. This makes conversions incredibly straightforward compared to, say, imperial units with 12 inches in a foot, 3 feet in a yard, 1,760 yards in a mile.
Much less calculation needed.
Far less. That's why it's the required language of science worldwide. Experiments published in journals use metric units, SI units, so results are consistent, comparable, and replicable anywhere, and in global trade or manufacturing. If you're designing parts in one country to be assembled in another, using metric ensures everything fits. Any company working internationally has to be fluent in metric, often converting from older, local imperial measures.
Global standard for consistency. Okay, now for the more specialized units. These often show how measurement evolves based on specific industries or historical needs. This context is really key for C1 understanding, isn't it?
It really is. It shows you understand not just the unit, but its world.
Let's group them. First, volume and capacity, barrel, pint, and quart. Now, barrel. That one sounds very industry specific, particularly oil. Hugely so. The standard oil barrel is a very specific volume. 42 US gallons, which is about 35 imperial gallons or roughly 159 liters. This isn't just a unit, it's the unit for global oil trading. When you hear news reports about the price of oil fluctuating, it's almost always quoted per barrel. And those benchmark prices you hear about West Texas Intermediate, WTI, or Brent crude, they're priced per barrel. Massive financial decisions hinge on this single unit. It carries enormous economic weight. Wow. Okay, so barrel in that context isn't just any old barrel.
Not at all. Although confusingly, a barrel for measuring beer can be a different size. But the oil barrel is king in finance.
Right. The more everyday ones, pint and quart. A pint is 16 fluid ounces in the US, but different in the UK.
That's right. The US pint is 16 fluid ounces. The UK imperial pint is larger, 20 fluid ounces. It's deeply embedded in social customs. Ordering a pint of beer is common in many countries. But it also appears in recipes and for smaller liquid measurements.
And a quart, that's bigger than a pint. Yes, a quart is 2 pints. So 32 US fluid ounces, which is actually quite close to a liter, about 0.95 liters. You often buy milk or motor oil by the quart in places using the imperial system. Using pint and quart correctly shows, both the standard metric units and these culturally specific traditional ones.
Okay, moving from volume to strength or potency,
Yeah.
proof. This is only for alcohol, right?
Exclusively. Proof is a scale used to measure the alcohol content, the strength, of distilled spirits like whiskey, vodka, rum.
And it's not the same as percentage. I've heard 100 proof doesn't mean 100% alcohol.
You heard correctly. The system varies slightly, but in the United States, the proof number is exactly double the alcohol by volume ABV percentage. So a spirit labeled 100 proof is 50% ABV. 80 proof is 40% ABV. The history is quite fun. The original British test involved mixing the spirit with gunpowder. If the mixture could still ignite, the spirit was deemed above proof. Today it's measured chemically, but the term persists, especially in the US market. Knowing it means understanding that specific industry jargon.
Double the percentage. Got it. Okay, shifting to area in distance units. We absolutely must cover the hectare. Seems crucial for land measurement.
It is, especially outside the US where the acre is still common. A hectare is a metric unit of area, defined precisely as 10,000 square meters.
Yeah.
That's equivalent to a square that's 100 meters by 100 meters. It's the standard metric unit used internationally for measuring large land areas, farms, forests, parks. Global organizations like the UN Food and Agriculture Organization use hectares in their reports for comparing land use across countries because it fits neatly into the decimal metric system, unlike the acre.
10,000 square meters.
Yeah.
Okay, and then a much less precise one. Pace. This is literally a step.
Pretty much. A pace is the length covered by one normal step, or sometimes a double step. Obviously, it's highly variable depending on the person. But historically, it was incredibly important. Before modern surveying tools like GPS or lasers, surveyors often estimated distances by pacing them out. They'd calibrate their own average pace length and count steps to map land boundaries.
So a very human, very approximate unit.
Exactly. The Roman army even used a standardized pace, about 5 Roman feet, as a unit for measuring marches. It's a great reminder that measurement systems evolve and were once much more tied to the human body.
Fascinating. Okay, last pair. Power and speed, horsepower and miles per hour, mph. Horsepower measures engine power.
That's its job. Whether it's a car engine, a boat motor, or an industrial pump, horsepower is a common unit used to quantify the rate at which the engine can do work. More horsepower generally means more speed, more acceleration, more capability. Car enthusiasts and engineers talk horsepower constantly.
The benchmark for engine performance. And miles per hour, mph. That's velocity.
The standard unit for speed, specifically in countries using the imperial system, like the US and UK. Road speed limits are posted in mph. Car speedometers show mph. It also gets used in other contexts, like meteorology. The speed of wind, especially the sustained wind speeds defining the categories of hurricanes, are often given in mph.
Okay, and let's squeeze in one last, rather archaic unit before we wrap up. Score. Not points in a game, but the other meaning.
Yes, that lovely old word. A score means a group of 20, or sometimes approximately 20.
Like in Lincoln's Gettysburg Address. 7 years ago, meaning 87 years.
Exactly. 4 score is 4 times 20, which is 80 plus 7. You might still encounter it in literature or very formal speech. A score of volunteers arrived, meaning about 20 showed up. Or someone might refer to 70 years. as a way of talking about a typical human lifespan, echoing biblical phrasing.
So recognizing that meaning score equals 20 is a sign of a pretty sophisticated vocabulary?
It definitely shows a deeper grasp of English history and usage. Yes, a nice one to know. Hashtag out TRO. Connecting in final thought. So looking back at this deep dive, we've really journeyed through the landscape of mathematical language. We started with defining the precise diameter needed for an engineering project. We moved through understanding how an economic function can model market trends. We considered the importance of achieving minimal error in scientific results. Mastery of these terms, these 35 plus concepts, it genuinely transforms your ability to analyze situations, to quantify observations, and crucially, to describe the world with much greater precision in English.
Yeah, it feels like you move beyond just, solving for X in a textbook. You're equipped with C1 language to express those really complex relationships between different variables. You can argue for using the metric system in a global business report, understanding why it matters. You grasp the real financial weight behind a shift in the price per barrel of oil.
Exactly. You're connecting the analytical thinking of mathematics directly to powerful, nuanced English communication.
The goal isn't just getting the right answer, but being able to explain it clearly and effectively.
Precisely. It's about insight. And the language of mathematics provides such clarity, especially when things get complex.
Well, since this has hopefully added up for you and multiplied your lexical skills, we do want to leave you with one final thought to sort of chew on. Given how many of these terms we discussed have those powerful dual meanings, like dividend being totally different in math versus finance, or factor meaning a number component or a causal element, what other mathematical concepts do you notice sort of bleeding over? Where else do you see math language popping up in everyday talk or business jargon or even maybe psychology? Something to think about. Keep quantifying knowledge. And please remember to like, share, and subscribe to this YouTube channel. Thank you for joining this deep dive.